Okay, a few more notes on mechanical energy. We talked about how it's conserved, and what that really means when you look at it from an equation standpoint is that mechanical energy initial is equal to mechanical energy final. Now you want to break that down a little farther, and you get kinetic and potential. So the kinetic energy initial plus the potential energy initial will equal the kinetic energy final plus the potential energy final, meaning that before something happens, the mechanical energy will equal the mechanical energy after something happens. So if we think more specifically on like a falling object question like Bob falling off that bridge, if we look at something like that and we start talking about energy at the top and bottom, and we start thinking somewhere along the lines of these formulas here, right there, where you've got the kinetic energy at the top, potential energy at the top, kinetic energy at the bottom, potential energy at the bottom. And you start thinking about the variables that go with that. If Bob is just falling off the bridge, like he was in the bell work yesterday, if Bob is just falling off a bridge, he's going to have no initial kinetic energy because his initial velocity is going to be 0. At the bottom, his height would be 0. So he'd have no initial or no final potential energy, which just leaves the middle of the problem standing there, where the initial potential energy would end up equaling the final kinetic energy. Now, in all truthfulness, if something starts out with a kinetic energy, and it's entirely possible. You think of swim team people, they dive downward into the pool. You could very well have an initial downward velocity, and that's no problem. You put it in right there, and it works out just fine. But when you start looking at this from a math standpoint, what happens with your m's, with your masses, is that in math, it's all the same mass. So all those masses disappear. And then you say, okay, 1/2 of the velocity squared, there's a plus that should be there. 1/2 velocity squared plus GH is equal to 1/2 of VF squared. And if you do a little mathematical solving there, you're going to multiply both sides by 2, which dismisses the half here. It dismisses that half there and puts a 2 there. And if I'm not mistaken, right about there is going to be a formula. Nope, I am mistaken. The formula is not there. Bummer. That's just a box. Well, what it boils down to is, here, I'll do this the hard way. No problem. Magically. What you get when you start canceling out the m's, you get rid of those halves and make a 2 there because of the way the math works out. And we have a formula that we have seen before. VF squared equals VI squared plus 2GH. And while it's not a new equation, it's an equation we've had since chapter 2, it shows you why it exists. This equation exists because of the conservation of energy. If I fall from a given height with a given acceleration, and maybe there's initial velocity involved, I will end up going a certain speed. So if you go back to that problem where Bob was falling off the bridge, he fell 20 meters. If you put 20 meters in here and solve it, if he falls 20 meters, he's going to end up with a certain speed. I can't recall what it was. Wasn't it like 19.8 or something like that? But given a certain height, you'll end up with a certain speed, and that's what mechanical energy does for us. It's a wonderful, wonderful thing. And one more wonderful thing is, of course, this. Oh, look, there's a homework assignment hiding right there. Right there. See? Right there. See it? 171, 1 through 5. Enjoy.